Rob Schapire, who I've known for over 20 years now, since he was my undergraduate advisor. But he's also, I guess he was a student at MIT at the same time, and also with Ron, as Avram. And Rob is, of course, known for many things, boosting the EXP algorithms, a cool application of Maxent, and too many things that I can't list, but I'm happy to, introduce them.
Thanks, Lev. I want to start by wishing a happy birthday to Avram, who, as Lev said, I've known for a very long time, almost 4 decades now, since we were grad students at MIT in Ron's group. And there's something about Avram that always makes me kind of smile to myself, even just thinking about him. I think it's because he has such a good nature and good-heartedness, and he's got such a kind and gentle spirit. So I want to say congratulations to Avram for your many, many really insightful and creative contributions to the field, and also for mentoring an amazing line of really outstanding students, so happy birthday. So I want to talk about Astral space, which is a way of studying convex analysis at infinity, something rather different than what we've heard about so far. And this is joint work with Miro Dudik and Matus Telgarsky. So this talk is about convex functions and minimizing convex functions, which is obviously a very important problem in machine learning and statistics and many other fields. And when we think about convex functions, we're likely to think about a function like this parabola over here, and it's rather common to assume that the function attains its minimum at a finite point, like this parabola does, of course. But actually, the problem we're looking at is that some convex functions have no finite minimizer. Like here's the exponential function, which I'll talk more about in a minute. And a function like this can only be minimized by a sequence as that sequence heads to infinity. And this certainly happens in cases of practical interest. It happens in things like boosting. It can happen in maximum likelihood, maximum entropy, logistic regression. So this can actually come up. And the problem is that analyzing convergence of algorithms in these kinds of cases is often more challenging. I'm not saying it's impossible, but it often requires using these carefully tailored techniques. And so what we're trying to do in this work is to develop a theory for studying these kinds of minimizers at infinity. So to give some intuition, let me start by talking about the exponential function, as I already mentioned. And as I said, there's no finite point where this function is minimized, where it attains its minimum. And so instead, this function can only be minimized by a sequence as that sequence heads to negative infinity in this case. And so intuitively, we kind of wish we could say that the function is minimized at negative infinity. And mathematically, there's a way we can do that. What we can do is we can take the real numbers and we can extend them to include plus and minus infinity. So that gives what's called the extended reals, which I'll write as R bar, which is, again, is just the reals with plus minus infinity. And then we can take this function and extend it to the extended reals in kind of the natural way, where you define the function to be 0 at negative infinity and positive infinity at positive infinity. And if you do that, then the function you end up with is, well, it's a continuous function. It's continuous over the extended reals. And whereas the original function did not attain its minimum, this extended function does attain its minimum at negative infinity. And the function kind of still feels convex. So there isn't a way at this point of defining convex functions over the extended reals, but kind of feels convex. And it kind of feels like we can do things like extend derivatives so that the derivative at negative infinity would be equal to 0, and then you would still have this regularity condition for convex functions that they attain their minimum exactly where their derivative or gradient is equal to 0. So in one dimension, all of this stuff seems really pretty straightforward. How to add points at infinity, because there's just plus minus infinity, and how to extend functions to this larger space in a way that captures minimizers at infinity. But in 2 or more dimensions, it's much less obvious how to do this. And that's what this work is trying to get at. So what we're trying to do in this work is to take Euclidean space, Rn, and extend it to include these points at infinity. And what we're trying to do is to reveal the structure of how convex functions behave at infinity. And we're trying to build up foundations so that we can do things like prove convergence of algorithms. And what we're trying to do is to make the study of convex functions more complete. So for instance, so that every convex function, when you extend it to this space, has a minimizer, actually attains a minimum. And we're trying to do it in a way that's compatible with convex analysis. We're really trying to extend convex analysis itself. Okay, so what we do in this work is we introduce this thing called Astral space, which is an extension of Euclidean space that includes these points at infinity. And we look at how to extend functions on Euclidean space to Astral space. And we're also studying all kinds of topics from convex analysis, because as I said, what we're trying to do is to extend convex analysis itself. Okay, so here's an outline. I'll talk about what minimizers at infinity can look like, how to construct astral space, what points in that space look like, and then how to extend functions to astral space. Okay, so before I dive in, just a tiny bit of notation so we're all on the same page. So I'm always using n for the dimension of the space we're working in, so we're working in Rn. So I'll denote scalars just in italics like this, whereas vectors, points in Rn, are written in bold like this. So in particular, a tuple is written in bold, but then its components are in italics, x1 through xn. So you can tell by the font what the type is. And in this talk, all sequences are always indexed by t, so t runs 1, 2, and so on. So limits and convergence are always as t goes to infinity. And then I'm writing xt in parentheses to denote a sequence. Okay? Okay, so what can minimizers at infinity look like? So so we're given a convex function f defined on Euclidean space. And it can be real valued, or it can take plus minus infinity as values. And as I already said, if it has no finite minimizer, then it can only be minimized by a sequence going to infinity. So what can those minimizers at infinity look like? So in one dimension, as I already said, the only possibility is it can converge to plus minus infinity. But when you're in 2 or more dimensions, there are many more possibilities. So let's look at some examples to build up some intuition. Okay, so here's a particular function that I've written down algebraically on 2 variables, x1 and x2. And here's a plot of the function. So the top part is showing this is a surface plot of the function, and the bottom curve is a contour map. So showing, it's kind of like a topographic map showing the hills and valleys and so on. Okay, so how would you minimize this function? Well, to minimize the first term, we need to let x1 go to positive infinity. But to minimize the second term, we need the difference between x2 and x1 to go to 0. So in other words, you kind of have to, you need x1 to be going to infinity, but you also need x2 to be going to infinity at the exact same rate, or asymptotically the same rate. So for instance, you could let x1 and x2 both be equal to t, and then just let t go to infinity, which is to say that you're creating a sequence like this with pairs tt, which I plotted here, 1, 1, 2, 2, 3, 3, and so on. So you need to follow this diagonal valley. Yeah?
Why aren't you extending the inputs to be x bar also? So that the x1 and x2 could be infinity, exactly. Is there a good, like, I'm sure you thought.
Okay, well, at this point, we're just starting
Okay.
with a function on Euclidean space, and then that's where we're going to go. We're going to go to extending the, both the space and the functions.
Related to that is, why would you extend the range before extending the domain? Like,
Oh, the range, extending the range of the function is, that's just already standard in convex analysis. They typically use R bar. Yeah, so that part is standard. Is there another? Okay, good. So the point is that it matters how this sequence goes to infinity. So if you head in a different direction, then you won't minimize this function. And offset also matters. If you take the same sequence and just shift it over, you also will not be minimizing this function. Okay? Okay, so let's look at another example. So in that example, you could minimize this function just by following a straight line to infinity. So is it the case that every convex function can be minimized along a half line by following a straight line?
Whose law is it that the answer's got to be no?
Yeah, the answer is no. The answer is no. So here's an example of that, kind of similar in some ways. Sum of these two exponentials, and here again is a plot. So to minimize this function, well, to minimize the first term, again, we need x1 to go to infinity. To minimize the second term, we need x2 to be going to infinity, but it has to go to infinity much faster than x1 is going to infinity, so that this exponent here will be going to negative infinity. Okay, so for instance, one way of doing that is you could look at pairs t comma t squared. So the first term is t, the second is t squared, which follows this parabola off to infinity, and it's possible to argue that that does minimize the sequence. So by following a parabola, you can minimize this function, but it's possible to prove that there's no minimizing sequence that follows a half line to infinity. Okay, so how can we construct a space that captures these different kinds of minimizers at infinity? Okay, which brings me to the second part of the talk. Okay, so these sequences to infinity don't converge because there's nothing out there at infinity for them to converge to. So the idea to construct this larger space, the idea is to add new points to Euclidean space, which can become the limits of these kinds of sequences. And in order to do that, we need to be able to answer two critical questions. So the first question is, which sequences should have limits? And secondly, when should two sequences have the same limit? And if we can answer both those questions, then it's fairly straightforward to construct this enlarged space. Because what we can do is we can just add new points to become the limits of all of the sequences that are supposed to have limits. And we can do it in such a way that if two sequences are supposed to have the same limit, according to the second question, then they actually will. So we just add one new point for every group of sequences that are all supposed to have the same limit. Okay, so the main thing is We just have to be able to answer these two questions. So let's look at some examples for some intuition. So again, the first question is, which sequences should have limits? Well, the simplest kind of sequence for going to infinity is just to follow a straight line, just to follow a ray to infinity. There were coordinate axes which have disappeared.
They're visible on this one.
Oh, okay. Right, so the simplest way of going to infinity is just to follow a straight line, a ray to infinity. And so surely that should have a limit. So here's an example of one. So which sequences should have the same limit as this sequence? Well, there are some obvious answers to that. There are some obvious examples of that. So for instance, if we just change the rate at which the sequence is going to infinity, but still following that same ray, then surely that should have the same limit as the entire sequence. But here's a less obvious question. So here's our original sequence, which has a limit. But suppose we take that sequence and just shift it over by a fixed offset. And I'm doing things algebraically down here and geometrically up here. So we just shift it by a fixed amount. So surely this other shifted sequence should still have a limit. But should they have the same limit? Should those two sequences converge to the same point? And you could answer this either way. You could answer it either way. But we believe the answer should be no, that they should have different limits. Why? Because we've already seen that offset matters for minimization. We saw an example of that. And also in the kind of applications we care about, we often do care about an offset term. It's not that we only care about the overall direction of minimization, we also care about offsets. Okay, so how can we capture these intuitions? In this work, what we've done is to adopt a basic principle. The principle is to focus on limits in every possible direction. So in other words, to focus on one-dimensional projections of the sequences that we're looking at, on one-dimensional projections. So let me show you what I mean with an example. Okay, so here again are these two parallel sequences, and they have limits, and we want to know if they should have the same limit. So to answer that, what we do is we pick various directions, and we project them in those directions. So for instance, we could start with a vector like this one, which is just a unit vector pointing to the right. And then we can take the first sequence and project it down onto a line that's parallel to that vector. Okay, and we get a sequence like this. And algebraically, all we're doing is computing inner products, which are converging to positive infinity. And then we do the same thing with the second sequence. And that one also converges to positive infinity. So these two projected sequences have the same limit. But according to this principle, we can't just pick one direction. We need to consider all possible directions. Okay, so we can pick another direction, like this one. Okay, and now if we project the first sequence, everything projects down onto this point. For the second sequence, everything projects onto a different point. And you can see it algebraically also by computing inner products. So these two sequences, when projected, have different limits. And so therefore, since they have different limits in some direction, we'll decide that the two sequences, the sequences themselves, have different limits. Okay? So to summarize, so the two questions again, which sequences should have limits, and when should two sequences have the same limit? So which sequences should have limits? Well, we answer that as exactly those sequences that converge in all directions is the phrase that we use. Meaning that when we look at these inner products, which are just the projections of the sequence in a direction u, when we look at those inner products, the limit of these projections of these inner products exists for every possible direction u. And then when should two sequences have the same limit? Well, we answer that by saying exactly when they are all directions equivalent is the phrase that we use, meaning they have the same limit in every direction. So these limits that we've been looking at exist and are equal for every vector u. Okay? Yeah.
Okay, so I understand the principles, but do they apply also if you have sort of, so I would like to think of it that you're extending convex sets, which are sort of bounded convex sets. So it seems like you are extending them, right? Sort of, those two principles should work for any bounded convex set, compact
Well,
set. So,
first we extend the space, and then we're going to,
well, if it's the bounded convex set, you don't need to extend anything, right?
right, but we don't necessarily only want to work over bounded convex sets.
No, so I'm asking whether for bounded convex sets we get what we expected to, but nothing really changed.
Yeah, well, okay. I think a simpler thing is that just individual points are going to have, when you extend the space, you're still going to get Rn as a subspace of this larger space.
Okay.
So if you have like a bounded convex set, it's just going to stay, it's not going to change at all. Okay, so Rn itself, Euclidean space itself is not changed with this. But you do get a lot of points at the at the edges, so to speak, at infinity. Okay, so yeah, so when we take Euclidean space and we expand it according to these criteria, that's what astral space is, and we write it as Rn with a bar over it. Okay, not R bar to the n, which would be different. This is Rn with a bar over it. Okay, so in one-dimensional, you're just adding plus minus infinity. So one-dimensional astral space is the same as the extended reals, as you expect. And we can update our notation. So we write scalars and vectors, as I said already. And now we have a third kind of object, which are points in astral space, or astral points. And those are written in bold with a bar over them. Okay, bold with a bar. Yeah.
Is it homeomorphic to the n-dimensional sphere?
No, it's not. Okay, so that would be a different kind of a construction. That would be called cosmic space as opposed to astral space. Okay, and and which has different properties. Yeah.
So a spiral wouldn't have a limit, something like that, right? That goes outward. That would that.
Correct. Correct. Okay. Okay, so let me mention some topological properties. So first of all, this space is compact, okay, which is very nice mathematical property, very powerful, and it's especially helpful for proving convergence of iterative algorithms. Another very nice property is that every linear function can be extended continuously to the space, and hopefully I'll have time to explain what I mean by that a little bit later. But what that means is that anything linear is likely to behave nicely when we extend it to astral space. And that's especially relevant to convex analysis, which is very heavily built on linear stuff. So it means you can generalize linear maps, hyperplanes, half spaces, which are clearly all linear. But then you can also extend things like what it means for a set or a function to be convex, and you can extend conjugates, in differential theory. All these things extend nicely to this space. And this space is not a vector space or a metric space. So it does require kind of a different way of thinking, since you're used to thinking of metric spaces. But all the same, a lot of other stuff works out. Okay, so what are points in this space like? So as I said already, the simplest sequence to infinity is along a ray. Okay, so in other words, sequences that have the form t times v, where v is just a fixed vector. And a sequence like this converges in all directions. It's not hard to prove that. So therefore, it has to have a limit in astral space. And that limit is called an astron. So a general point in astral space is called an astral point. An astron is one particular kind of astral point. And we write it as omega v. V, again, is this direction that you're heading in. Okay, so it's just the limit of that sequence. And astrons are especially important because they turn out to be the building blocks of all astral points. So let me show you what I mean by that with another example. So here's a different example of a sequence. So let's say we pick 3 vectors, v1, v2, and q. And then we form a sequence like this, t squared v1 plus t v2 plus q. So it's like you're starting at q, and then you're following a parabola off to infinity, okay, where the parabola is defined by v1 and v2. So intuitively, this sequence is converging to infinity clearly most strongly in the direction of v1, overwhelmingly in the direction of v1. But it also has this secondary convergence to infinity in the direction of v2. And then there's like this fixed offset by q. So intuitively, that's what's happening. And again, this is just an example. It's not that all sequences we care about have this form. It's just an example. So a sequence like this converges in all directions. So it has to have a limit in astral space. And it turns out that we can write that limit in a particular form. We can write it like this. So omega v1 and omega v2 are the astrons, and q is just the vector q. And then there's this funny looking plus sign with a dot next to it, which is an operation called leftward addition, which is similar to vector addition, but it doesn't have all properties. In particular, it's not commutative in general. And it gives a kind of dominance to the term on the left, which is why it's called leftward addition. So it turns out that every astral point can be written in that kind of form. Every astral point can be written as a leftward sum of astrons and with a finite part. And what's more, you can always choose these vectors, v1 through vk, to be orthonormal. And we can choose q to be orthogonal to all the vi's. So every point in this space can be written in this form. And this number k, the number of astrons you need to represent the point, is called the astral rank. So astral rank 0 are just the points in Euclidean space, and astral rank 1 are the ones that you can reach by following a straight line. Okay, so
It has to be finite?
the number of astrons? Yes, because you can always choose these to be orthogonal, orthonormal.
Okay.
So actually, it'll never be more than n. Yeah.
And they're not weighted because you put any of the weighting into the finite part, is that right? Like, you would think that.
Well, they're not weighted because the way we're considering things going to infinity is not sensitive to things like constants or even how fast they're going to infinity. The only thing it's sensitive to is like the ratios. So like in this example, if you change these to, e to the t and log t or something, you would get the same point. Yeah?
Why does it have to be orthogonal? Free is not enough?
What was the last part of the question?
Why does it have to be orthogonal? Orthonormal.
They don't have to be orthonormal, but for any astral point, you can always choose them to be orthonormal. Okay, so yeah, you could still get a perfectly well-represented astral point without them being orthogonal, but then you can take that same point and rewrite it if you wanted to. Okay, so what time should I?
5 minutes.
Okay. Okay, so last part of the talk is on extending functions to astral space. Okay, so we're given a function f defined on Euclidean space, and we want to extend it to astral space. So how do we do that? Well, in the case of the exponential function, what did we do for the exponential function? So you're given this function, and we want to define the extension, which we would still write as would now write as f bar, and we want to extend it to one-dimensional astral space, which is the same as the extended reals. And before we said the extension at negative infinity should be 0. Why? Because for any sequence converging to negative infinity, the function values are converging to 0. And the same thing for at plus infinity. So this is really the only way to extend this function to the extended reals so that what you get at the end is continuous. So we can kind of generalize that. So again, we're given a function f, want to define its extension. So we're given a particular point x bar. How do we define that extension at x bar? Well, in kind of a nice case is when the limit of these function values exists and is the same for any sequence xt converging to that astral point x bar that we care about. And that's kind of the case that you saw in the exponential function. Okay, and in that case, it's only reasonable to define this extension at x bar to be that limit, which again is the same for any and every sequence converging to x bar. So this is an assumption. Okay, so it's not true in general. But if you're in that case, this is the only reasonable way of defining this. And if that holds for every astral point, then f bar becomes the only possible continuous extension of f to astral space. And so as a prime example, all linear functions have continuous extensions by construction. And so another example is diagonal valley, which turns out you can extend continuously to two-dimensional astral space. And so, yeah, maybe I'll skip. Well, yeah, let me move on. If the function does not have a continuous extension, then we have another way of defining its extension. Okay, so in the continuous case, we define its extension at its point to be the limit over all sequences. But in general, those limits might differ for one sequence or another. So a nice way of defining this extension instead is to define it as the minimum of these limits over all possible sequences. And that has some nice properties. One of the nicest is that whereas the original function might not attain its minimizer, might not attain its minimum, this extension always attains its minimum over astral points, since, and that just follows by compactness. Okay, so let me skip this since I'm short on time. An application of this, we can use this to prove the convergence of various iterative methods applied to various machine learning and statistical settings. So like we can use this Astral machinery to prove the convergence of gradient descent, coordinate descent, and other methods for things like logistic regression and boosting and maximum likelihood, all of which have continuous extensions, it turns out. And the important thing is that you can prove this convergence even in cases where the function does not have a finite minimizer. And let me just emphasize that these algorithms, it's just the regular algorithms operating on Euclidean space, but we're using Astral methods in the proofs. In particular, these proofs depend on Astral continuity properties, without which it turns out that these kinds of general results do not hold. Okay, so I'll summarize. I tried to give you a taste of Astral space, how to construct it, what Astral points are like, how to extend functions. We're trying to expand the foundations of convex analysis to encompass these points at infinity, to make it easier to do things like to give more routine proofs of convergence. And there's an awful lot that I did not cover, so this is going to be published as a book this fall. And you can, in the meantime, if you're dying to read it, you can download a draft of the book from this URL. That's it. Happy birthday.
Any questions?
Yeah.
Could there be any connection to non-standard analysis and some kind of theory of infinitesimals?
You know, I tried reading that, and not that I found, but maybe there's more to do there. And yeah, I think that would be cool if you could do that. Yeah.
So thinking about these extensions to infinity, sort of like one thing that usually bugs me is like log loss is unbounded, and sort of we don't get generalization bound if you just use log loss. Would this give us a way to go around these issues, or it's unrelated?
Yeah, I really don't know. I don't really see a way of doing that. They seem like kind of different issues, I think. Yeah, because that's about the function values themselves being unbounded. This is about the points that you're following being unbounded. Yeah, Lev.
I'm thinking, so if you're just running gradient descent and like e to the negative x, if you're not changing the algorithm, how does it find the point at negative infinity? I imagine gradient descent would do what gradient descent does, but you're saying it'll give you convergence.
Well, we can prove convergence. So we can prove convergence of the function values.
Oh, okay.
Or you can prove convergence within astral space. So there's some astral point that either the algorithm is converging to, or since it's a compact space, there has to be a subsequence that converges to an astral point.
But you would kind of want gradient descent to actually just output negative infinity, and that it's not going to do, right?
Right. Well, that would be, yeah, that would be, right. So, but you can say asymptotically it's converging to negative infinity or to, more general points.
Is there hope that you could change gradient descent when you're working explicitly over
Oh, to like
space?
jump to the limit?
Just jump to the limit, I mean.
Yeah, I don't,
Step size.
what?
It's just infinite step size.
I mean, that's what
Yeah.
you want eventually, right?
Yeah.
To actually for it to just say, okay, we're done.
Right. So I don't know. I mean, I imagine there are interesting computational issues if you actually try to do this. So we're used to thinking of Euclidean points that, you can always approximate a Euclidean point by a rational, with rational numbers, you can approximate it arbitrarily. Well, the same is not true for these points at infinity. So if you have like two astrons and their associated vectors are really, really close, the astrons are still infinitely far apart. So you would need an infinite precision computer to approximate. You can't approximate these points, basically. Yeah.
Yeah, I mean, going out, isn't that a bit like asking gradient descent at some point after a finite number of steps, just jump to your to the
Yeah, that's
finite
true,
solution?
too.
I mean, you can't do that, right? You can only approach it. And I mean, this is.
Right.
I mean, why doesn't gradient descent just jump to the right solution for finite? What?
Well, I wouldn't ask gradient descent to do it. I would ask a different algorithm.
You can do some
Astral
quadratics,
descent.
right? Once you go beyond quadratics, you
Yeah.
can't, right?
Yeah.
I mean, it's.
Yeah.
Should I think of astral points almost in bijection with affine spaces or something like that?
Well, astral points, I mean, there are different ways of thinking about them. I mean, you can think about them as these limits of sequences. Another way of thinking about them is you can identify them with functions over functions over Euclidean space. So you can basically think of each astral point associated with basically the limits of these sequences that I talked about. And so it's like a dual representation of each of these points. And then the astral points correspond exactly to those functions that are convex and concave and that are equal to 0 at 0. So it gives a very exact correspondence, yeah. Yes?
Do you have any notion of distance from astral points when you talk about convergence from?
No, it's not a metric space. So it's provably not a metric space. So you can't define the astral topology based on any kind of distance. Yeah. But there's kind of like these one-sided distances that you can, I mean, it's not a real distance, but yeah.
Last question.
I have like sort of a meta question. I really enjoyed the talk. I feel like the axioms you need and like sort of the limit point definitions, they feel very fundamental. And I was almost surprised this wasn't studied at some point in like the foundations of real and convex analysis. So do you have like an inkling for why people didn't go after this in the past?
Well,
like the motivation for the iterative algorithms wasn't there, like.
Okay, well, okay, so what we're doing is we're compactifying Euclidean space.
Yeah.
And so there's certain, mathematically, this is not at all the first compactification of Euclidean space. And so ours actually turns out to be a special case of a family of compactifications that has been studied mathematically. Within the context of convex analysis, the one that people actually have really looked at is this convex cosmic space that I mentioned before, which has different properties. So it is homeomorphic to it's equivalent to taking Euclidean space and shrinking it down to the unit ball, the open unit ball, and then closing it, and then all those points become points at infinity. And so it is a metric space, but you can't do things like extend linear functions continuously to it. And so, Rockefeller and Vetz have studied that quite a bit, but otherwise, I don't know. I don't know. I guess it was, these compactifications, it depends what you want to use it for. And so if that was good enough, then do that. And then for these algorithms, it seemed like this was a better fit.
That seems like the answer, right? It's like these algorithms. Very important. Thanks.
Let's thank Rob
Okay,
again.
thanks.
And let him and everyone else go to lunch.
Yeah, yeah.